All right. We are in chapter 3. We are in chapter 3. So start a new section in your notes. Whatever you need to do to make things organized, we are here. Okay. So we're going to start into this funny word that's called stoichiometry. It's one of the best words in all of science, I think. But yeah, we're going to look at stoichiometry, what it is, how we go from there. So this first slide is something that we will actually do when I arrive back. So we will do that together, and we'll start right into our notes. So that first slide is kind of the idea of how scientists have determined the mass of an atom, and how we're going to determine the mass of, it says gummy bears, but we'll use some Swedish fish, and how we'll determine a pretty scientific way to develop or to anticipate the number of grams of a Swedish fish, or in this case, an atom, as scientists have researched. So that is what we're kind of looking into. So the basis for atomic masses comes from this system called based on carbon-12. That is the standard. So in this system, carbon-12 is assigned a mass of exactly 12 AMU, atomic mass units, and the masses of every other atom on the periodic table is given relative to this standard. These are specific atoms here, not like a gram of this material also. So there are different ways to analyze that we'll talk about a little bit later. But this is specifically an atomic mass unit. So one atom of carbon-12 weighs 12 atomic mass units. The way they originally kind of did this scientifically is using a mass spectrometer, which separates atoms with different masses and gives pretty accurate values of those relative masses. So here's kind of that process where a sample is pressed through this tube, it is ionized so that there are only ions, and then it's accelerated. As it's accelerated, they're pressed through a magnetic field. Those that are heaviest move the least, kind of based on inertia, right? If something's going in one direction, the heavier it is, the more difficult it is to move, or the greater mass, rather. And then they go up to this detector plate, and you can kind of determine relative masses from that detector plate. And it produces, when they put in carbon-13, which is an isotope of carbon, it has 7 neutrons and only 6 protons. That isotope is found to have a relative mass of 1.0836129 from carbon-12. When we use that value of the ratio between carbon-13 and carbon-12 masses, we can actually just use that dividend, the 1.0836129, and multiply it by 12 atomic mass units to give us the relative mass of carbon-13. When we do that, we find 13.003355 atomic mass units, which kind of goes into why carbon-13 is called carbon-13. We attribute it to having 7 neutrons instead of 6 neutrons like carbon-12 has. Other atoms' masses are found in a really similar manner and reported as the atomic weights listed on the periodic table of elements. So every atomic weight that we'll be using in chemistry is based off of this carbon-12 base model, where everything else is relative to that. Also note that while we assume carbon to have exactly a mass of 12 on the periodic table, its mass is listed as at 12.01. And so the question is begged, why is that? And the answer is because we have multiple isotopes of carbon that exist in nature. So carbon-12 is the most rampant isotope of carbon, but carbon-13 and carbon-14 both exist in nature. And so what we do to represent that number, no carbon atom has a mass of 12.01, but we take the average of the masses of all the carbon isotopes as they occur relatively in nature, and we take their average based off of how greatly or how often they occur in nature, and that's the average that we use. They have the same properties. Isotopes don't change property-wise when it comes to isotopes of a given element, so we have to account for all of those isotopes when we're representing the mass. on the periodic table. So those isotopes have 6 protons, but they have 6, 7, and 8 neutrons respectively. The listed atomic mass is the average of the atomic masses of all 3 of the naturally occurring isotopes of carbon, and that average is 12.01. It's important to note that none of the single carbon atoms have the mass of 12.01. They'll have only 12, 13, or 14 because it's just the sum of the protons and neutrons. Remember, electrons are not massive enough to account for the mass of those atoms either. However, in stoichiometry, we will use the number 12.01 because we can assume that we'll have a similar to average makeup of carbon atoms as the calculation that produced 12.01 atomic mass units for carbon's average mass. So the way carbon exists in the atmosphere is basically how, or in life around us, in terms of those isotopes, is what we can assume we will have in the makeup of any stoichiometry or chemical reaction that we have using carbon. So here is a little option that you could have for the practice of finding an average mass of an element. So copper, for example, is shown from a test in a mass spectrometer to have copper 63 isotope of having 62.93 atomic mass units, and copper 65 is having an atomic mass of 64.93 atomic mass units. So scientists have found that in 100 atoms, 69.09 of them are copper 63 and 30.91 of them are copper 65. So the question is, what is the mass of 100 copper atoms? And what we can do is we can go ahead and just look over here and say, okay, if 69.09 of them have this mass, I'll just multiply those two numbers together. And if, let's say, 30.91 of them have this mass over on the right, then I'll multiply those two numbers together. Ooh, and these are AMU as well. And that will give me the mass of 100 of these copper atoms. So 62.93 times 69.09, that gives me 4,347.837. And I have 64.93 times 30.91, and that gives me 2,006.9863. Now, when I add those two numbers together, it gives me It gives me 6,354.82 atomic mass units for 100 atoms. So the next question is, based off that, what's the average mass of one copper atom? And if we go back to this, we can say, okay, I'm going to take this and divide it by 100, and that should give me the mass of one copper atom. So it should be 63.55 approximately atomic mass units. And if you look at your textbook on the periodic table, you should see that same value represented there. So that's how we can kind of use that average to figure out what the average masses are. Now, we would also have to check, does that answer make sense? We know that the number should be larger than 62.93 because that's the low end, and it should be smaller than 64.93 because that's the high end. Our answer really should fit between those numbers. It does. And that's a good thing. So that's just kind of a quick logic check, right? So now let's talk about a new concept called the mole. Because matter contains such an immense number of atoms, we use a unit of measure called the mole for counting those atoms. It's also abbreviated as MOL. I know it's a little goofy, but don't abbreviate it just as M, because just M means something entirely differently. So we will abbreviate it, if you want to abbreviate it, as MOL. So we're using this value to represent infinitesimal atoms, basically so small that we've never seen an atom itself, right? So these are very, very small things. So we have to represent them in a way that makes sense for when we say I have 10 grams of carbon. That's something I could hold in my hand and see visibly, right? But that thing contains an enormous amount of atoms because those atoms are so small. This is our conversion unit from those teeny tiny individual atoms to a mass that we can actually functionally use in a lab. So that number then is going to be relatively large. Now, this is actually the number equal to the number of carbon atoms in exactly 12 grams of pure carbon-12. So we have this scale that goes from atomic mass units to grams. And in fact, what ends up happening is we would say, okay, if there are 12 atomic mass units, there are also going to be 12 grams as we relate those from moles to grams. Now, this is used from a number called Avogadro's number, and it is defined as there are 6.022 times 10 to the 23rd atoms in that amount of carbon. So in 12 grams of carbon, there are 6.022 times 10 to the 23rd. That's 23 moves of this decimal space to the right. Okay, so this number is absolutely enormous, and it's our conversion factor to go from an atomic mass unit of an individual atom to say this has a mass of 12 grams. Okay, so here's the more simple version of it. Avogadro's number is equal to 6.022 times 10 to the 23rd. Now, you might ask 10 to the 23rd, what? And that is a great question. So 1 mole of something, no matter what it is, will always consist of 6.022 times 10 to the 23rd units of that thing. So here's an example. A dozen eggs has 12 eggs, right? A dozen donuts has 12 donuts. We use a dozen to say it has 12. When we're using Avogadro's number, we would say 1 mole of eggs has 6.022 times 10 to the 23rd eggs. Okay, so it's just another way to say it's this many of that thing. Okay, so a mole of Cheerios, 6.022 times 10 to the 23rd Cheerios. A mole of homework assignments, 6.022 times 10 to the 23rd assignments. 1 mole of donuts would be 6.022 times 10 to the 23rd donuts. So hopefully you're getting kind of the picture here. It's a very large number, and it can be used just like a dozen would be used, or just like a fortnight would be used. Well, actually, no, a fortnight is just 2 weeks. Scratch that one. But it could be used like a dozen, or it could be used like, I'm drawing a blank. It could be used like a dozen. So here is now a comparison of 1 mole samples of various elements, so we can see the mass of one of those moles. Now, remember, 1 mole of carbon-12 atoms is 12 grams, but things have different masses. So 1 mole of aluminum, which is the number of atoms present being Avogadro's number, 6.022 times 10 to the 3rd. So notice that this number does not change regardless of what compound or element we're talking about and regardless of its mass. Those two on the sides change, but the number of atoms remains the same. Okay, so those atoms are just greater in their density. A mercury atom is much more massive than is a carbon atom, or is an aluminum atom, or even a copper atom. Okay, so we can see that aluminum, 1 mole of aluminum has a mass of 26.98 grams, copper 63.55, sulfur 32.07, mercury 200.6, etc. These are all the values listed on the periodic table. Okay, this is the table just comparing real quick that the number of atoms present remains constant, the mass changes, the element changes. Here's also a visual. Those are Petri dishes that we have right there. And this is a visual of what 1 mole of each of these elements would look like. So they have various densities. Mercury is even a liquid at room temperature. But you can kind of get a picture that right there, think about a Petri dish. It's maybe the size of your palm, but that Petri dish contains 6.022 times 10 to the 23rd atoms of each of these elements. That's pretty incredible. That's an enormous amount. So, a mole is defined such that a sample of that natural element with a mass equal to the element's atomic mass will contain 1 mole of atoms when expressed in grams instead of AMU. So, the periodic table says carbon has a mass of 12.01 atomic mass units. That can also say it has a mass, 1 mole has a mass of 12.01 grams, okay? So that definition fixes the relationship between the atomic mass unit and the gram, okay? They're basically interchangeable. When we're talking about 1 atom of carbon-12, we're talking about 12.01 theoretical atomic mass units. When we're talking about 1 mole of carbon atoms, we are talking about 12.01 grams of carbon atoms, okay? So that's the idea here. Because of that, 6.022 times 10 to the 23rd atoms of carbon, each with a mass of 12 atomic mass units, so this is specifically carbon-12, it should be noted, it'll have a mass of 12 grams. If we just look at carbon as it's represented in nature, that's where the 12.01 grams comes into play. So essentially, 6.022 times 10 to the 23rd atomic mass units also is equal to 1 gram, okay? So that's where we can specifically say atomic mass units, Avogadro's number of them, equal to 1 gram. So if we then use some unit conversions here to go from carbon atoms to atomic mass units to grams, we can see, okay, I have 6.022 times 10 to the 23rd carbon atoms. These cancel right here. Pew, pew. I have 1 atom with 12 atomic mass units because that's the atomic mass unit of carbon, carbon-12. Then, pew, pew, I have 6.022 times 10 to the 23rd atomic mass units in 1 gram, so everything is canceled off except for grams. Even these right here, Avogadro's number of each of those cancel as well, and I'm left with just 12 grams. I'll show you kind of the shortcut for this in this example. So here's an example. It's on page 87 of your textbook. I would encourage you as you're working on your homework as well to refer back to these examples in your textbook. They will help you. So this is example at the end of page 87, and it'll go on to page 88. And it says americium, is an element that is manufactured in very small amounts using a device called a particle accelerator. Compute the mass in grams of a sample of americium containing 6 atoms. So the question, and this is up above one of those whiteboards as well, is what do we know, where are we going, and then the implied question will be how do we get there. So what we know we need to get is the mass of 6 americium atoms. We also know that the mass of 1 atom of americium is equal to 243 atomic mass units, and we get that from the periodic table where it's represented. So to find the mass of 6 atoms, if we have the mass of 1, we can just take that mass of 1 and multiply it by 6. Here also notice atoms and atoms cancel out. I'm left with atomic mass units. Now this number is relatively small because I'm dealing with the amount of atomic mass units. So I'm saying that this is only the mass of 6 atoms, right? Which I would never functionally use in a laboratory because that number is too small. They would still be very, very small. I wouldn't be able to hardly, maybe even see them with a microscope at that point. But we can also use the relationship with Avogadro's number to go from atomic mass units to grams because we want to know the mass in grams of these things. So we're going to use one more unit conversion in a way that will cancel off these atomic mass units, and pew pew, those atomic mass units are canceled off, and we have the mass of 6 americium atoms in grams. Now you can see this number is very small because now we're moving from a unit of atomic mass units to a unit of grams. Check. Does that make sense? It only contains 6 individual atoms, so we know the mass should be very, very small, and 2.42 times 10 to the negative 21st power is, in fact, very small. That small. That's itty-bitty, teeny-tiny, right? Okay, so I want you now to practice what is the mass of 200 carbon atoms, what is the mass of 200 rubidium atoms, and actually I'll show you, and this should be included on your homework. Sorry for that auto zoom. This should be included on your homework. I'm going to show you the carbon atoms, and then I'm going to let you free on rubidium atoms before you go and practice your homework assignment. But if I have 200 carbon atoms, I'm going to actually show you a shortcut because we've been using the atomic mass units to grams conversion. So atoms to atomic mass units to grams. Basically what I can say is I could say I know that 1 mole of carbon atoms is 6.022 times 10 to the 23rd, right? That Avogadro's number. Atoms, and that's in 1 mole, right? And then if I look at the periodic table, I can say 1 mole of carbon has a mass, and I'll go ahead and put labels on here of carbon, has a mass of 12.01 grams. Okay, so when I go ahead and I go from atoms here straight to moles instead, and that's actually the route I'm going to have you take so that you don't have to go to atomic mass units. We'll go from atoms to moles and then from moles to grams of carbon. So as I look here, carbon atoms cancel, moles of carbon even cancel, and I will be left with grams of carbon. So that what is the mass of carbon? I just go ahead and multiply 200 times 12.01, and I'll divide by 6.022 times 10 to the 23rd. I don't have a calculator on me right now, so you are going to have to plug that into your calculator. Include that on your homework, and include 161 rubidium atoms on your homework. You'll use the exact same process here up until this point, in which you'll use the periodic table value for rubidium atoms instead of the periodic table value for carbon atoms. That'll be the only thing that's different, and then you can plug that into your calculator and compute. Okay. You have some homework assignments that are posted on Google Classroom just to tell you the numbers. So go ahead and have a look at those and start working on them. Those will be due when I get back. Good luck.